the seventh live discussion session of the course Soil Mechanics Geotechnical Engineering 1 of this July-October session. This is the seventh discussion on the topic of shear strength, part 2. It's already time, but no one has joined. I'll be starting the dictation of the questions right now. I'll dictate all the questions. This session, this particular practice session, has only numericals, so it will take some time for all of you to solve. Those of you who are watching or will be watching. So I'll be starting right away. I'll first of all dictate all the questions. If anyone joins some meeting, he or she can start writing the questions from that point. After that, I'll give some time, and then after the break, I'll be discussing the solutions and explaining the concepts behind them. So this is the seventh live discussion session on Soil Mechanics Geotechnical Engineering 1. It's 5:04. I'm starting the meeting now, getting the dictation of the questions right now. So, okay. Of this chapter, Shear Strength 2, there are 16 numericals, mainly focused on the soil testing experiments in the laboratory, the triaxial tests, the unconfined compression test, and also one question on the pore pressure parameters of Skempton, which are obtained from after the triaxial test. Some questions might be repeated, but repeated from the previous live session also, but those are relevant to this chapter, this discussion also. It will be one or two maximum. Okay, I'll start now. The first question is, a cylindrical sample of soil having cohesion 0.8 kg per centimeter square and friction angle of 20 degree is subjected to a cell pressure of 1 kg per centimeter square. Calculate the maximum deviated stress at which the sample will fail and the angle made by the failure plane with the axis of the sample. We have a soil sample which is cylindrical, having a cohesion of 0.8 kg per cm square and friction angle of 20 degree. The cell pressure, it is in the triaxial test, is 1 kg per cm square. Whenever there is cell pressure, it is triaxial test. Now we have to find out the maximum deviated stress at which the sample will fail and the angle made by the failure plane with the axis of the sample. I'll repeat the question once. A cylindrical sample of soil having cohesion 0.8 kg per centimeter square and friction angle of 20 degree is subjected to a cell pressure of 1 kg per centimeter square. Calculate the maximum deviated stress at which the sample will fail and the angle made by the failure plane with the axis of the sample. Maximum deviated stress at failure and the angle made by the failure plane with the sample axis. Next question. An embankment 5 meter high is made up of soil whose effective stress parameters are C dash 50 kilonewton per meter square. 50 kilonewton per meter square and phi dash equal to 16 degree. These are the effective stress parameters. And gamma, there is a unit weight, is 16.2 kg per meter cube. Now the pore pressure parameters as found from triangle test are A and B. A and B are the Skempton's pore pressure parameters, which are requisite to find out the decrement or increment in pore pressure during the triangle test. Now this value of A is equal to 0.4 and the value of B is equal to 0.92. Find the shear strength of the soil at the base of the embankment just after the soil has been raised from 5 meter to 8 meter. Now the embankment height was 5 meter. After the height has been raised from 5 meter to 8 meter, we have been asked to find out the shear strength of the soil at the base of the embankment. Assume that the dissipation of pore pressure is negligible during the stage of construction and the lateral pressure at any point is half of the vertical pressure. So the shear strength is the only thing we need to find out, and pore pressure is negligible. That means we can find out the decrement or increment in pore pressure only with respect to the change inside the soil mass and not anything related to the dissipation of the pore pressure outside the soil mass. I'll repeat the question once. An embankment 5 meter high is made up of soil whose effective stress parameters are C dash equal to 50 kilonewton per meter square and phi dash equal to 16 degree and gamma, this unit weight, is 16.2 kg per meter cube. The pore pressure parameters as found from triaxial test are A equal to 0.4 and B equal to 0.92. Find the shear strength of the soil at the base of the embankment just after the soil has been raised from 5 meter to 8 meter. Assume that the dissipation of pore pressure is negligible during the stage of construction and the lateral pressure at any point is half of the vertical pressure. Here construction means raising the embankment height from 5 to 8 meter. Next question. A standard specimen of cohesionless sand was tested in triaxial compression and the sample failed at a deviator stress of 482 kilonewton per meter square when the cell pressure was 100 kilonewton per meter square under drained condition. Find the effective angle of shearing resistance of sand. What would be the deviator stress and the major principal stress at failure for another identical specimen of sand tested under a cell pressure of 200 kilonewton per meter square? Here we have specimen of cohesionless sand in triaxial compression with a deviator stress of 42 where it failed and the cell pressure was 100 under drain condition. Now we are asked to find out the effective angle of shearing resistance, the angle of internal friction. Now for another specimen which is identical, we have to find out the deviator stress and the major principal stress. The deviator stress and the major principal stress if the cell pressure is 200 kilonewton per meter square. For the first sample, only the angle of internal friction, and for the second sample, which is identical, to find out the deviator stress and the major principal stress at failure. I repeat the question once. A standard specimen of cohesion in the sand was tested in triaxial compression and the sample failed at a debated stress of 482 kN per meter square when the cell pressure was 100 kN per meter square under drain condition. Find the effective angle of shear resistance or the angle of internal friction of sand. What would be the debated stress and the major principal stress at failure for another identical specimen of sand tested under a cell pressure of 200 kN per meter square? Okay. Next question. A consolidated undrained triaxial test was conducted on a normally consolidated clay where sigma 3 equal to 250 kN per meter square, that is the cell pressure, and sigma del sigma d, that is the deviated stress at failure, is 275 kN per meter square. Determine the angle of friction in part A, part B, the angle made by the failure plane with the major principal plane, and part C, normal stress and shear stress on the failure plane. So we have a consolidated undrained triaxial test, CU triaxial test, where conducted on a normally consolidated clay. Sigma 3 is given, that is the cell pressure is given 250, and deviated distance of failure is given 275. To find out the angle of friction, the angle made by the failure plane with the major principal plane, and the normal stress and the shear stress on the failure plane. I'll repeat the question once. A consolidated undrained triaxial test was conducted on a normally consolidated clay. Sigma 3 equal to 250 kN per meter square. Sigma d del sigma df at failure is 275 kN per meter square. Determine the angle of friction, the angle made by the failure plane with the major principal plane, and the normal stress and shear stress on the failure plane. Next question. A particular soil failed under a major principal stress of 300 kN per meter square with a corresponding minor principal stress of 100 kN per meter square. If for the same soil the minor principal stress has been 200 kN per meter square, determine the major principal stress for part A, phi equal to 30 degree, and part B, phi equal to 0 degree. So the soil failed when the major principal stress was 300 and the minor one was 100. Now, if the minor is changed to 200, we have to find out the major principal stress for two conditions. First condition, when phi angle of friction is 30 degree, and when second condition, when phi angle of friction equal to 0. I'll repeat the question once. A particular soil failed under a major principal stress of 300 kN per meter square with a corresponding minor principal stress of 100 kN per meter square. If for the same soil the minor principal stress has been 200 kN per meter square, determine the major principal stress for part A, phi equal to 30 degree, and part B, phi equal to 0. Next question. In an unconfined compression test, a sample of clay 100 meter long and 50 millimeter, 100 millimeter long and 50 millimeter in diameter fails under a load of 150 Newton at 10% strain. Calculates the shearing resistance taking into account the effect of change in cross section of the sample. The size of the sample of clay is given 100 length and 50 is the diameter. The failure load is 150 Newton and the strain percentage is 10. To find out the shearing resistance, shear strength taking into account the effect of change in the sample cross section. The test performed is unconfined compression test. In an unconfined compression test, a sample of clay 100 mm long and 50 mm in diameter fails under a load of 150 Newton at 10% strain. Calculate the shearing resistance taking into account the effect of change in cross section of the sample. Okay. Next question. In a formation of cohesionless soil, the water table is at a depth of 3 meter. The degree of saturation is 50% and the average void ratio is 0.5. The specific gravity of the grains is 2.7 and the friction angle is 30 degree. Calculate the potential shear strength on a horizontal plane at a depth of 2.5 meter below the surface. Calculate the modified value of shear strength if the water table rises up to the ground surface. So we have a cohesionless soil formation where the water table is at a depth of 3 meter from the ground surface. The saturation is 50%, void ratio is 0.5, specific gravity is 2.7 and friction angle is 30 degree. We have to find out the potential shear strength on a horizontal plane at a depth of 2.5 meter below the surface. The first case, it is above the water table. In the second case, to find out the modified shear strength when the water table will rise up to the ground surface. So it will have two answers. I'll repeat the question once. In a formation of cohesionless soil, the water table is at a depth of 3 meter. The degree of saturation is 50% and the average void ratio is 0.5. The specific gravity of the grains is 2.7 and the friction angle is 30 degree. Calculate the potential shear strength on a horizontal plane at a depth of 2.5 meter below the surface. Calculate the modified value of shear strength if the water table rises up to the ground surface. So to find the shear strength in two separate situations, when the water table is at a depth of 3 meter and when the water table rises up to the ground surface, to find out the shear strength at a depth of 2.5 meter below the ground surface. Next question. Two samples of soil were tested in a triaxial machine. The all-round pressure maintained for the first was 2 kg per centimeter square and failure occurred at an additional axial stress of 7.7 kg per centimeter square. While for the second, these values were 5 kg per centimeter square and 13.7 kg per centimeter square respectively. Find the cohesion and angle of internal friction of the soil. So, in a triaxial test of two soils, the first case, the all-round pressure, that is the confining pressure, was 2 kg per centimeter square and at an additional axial pressure of 7.7 kg per cm square, failure occurred. While for the second, the all-round pressure or the cell pressure was 5 kg per cm square and at an additional axial stress of 13.7 kg per cm square, the failure occurred. We have to find out the cohesion and angle of internal friction of the soil. I'll repeat the question once. Two samples of soil were tested in a triaxial machine. The all-round pressure maintained for the first was 2 kg per centimeter square and failure occurred at an additional axial stress of 7.7 kg per centimeter square. While for the second, these values were 5 kg per centimeter square and 13.7 kg per centimeter square respectively. Find the cohesion and angle of internal friction of the soil. Next question. Yes. A cohesive soil has an angle of shearing resistance of 15 degree and a cohesion of 35 kN per meter square. If a sample of the soil is subjected to a triaxial compression test, find the value of lateral pressure in the cell for failure to occur at a stress of 300 kN per meter square. So we have a cohesive soil with an angle of internal friction 15 degree and cohesion of 35 kN per meter square. Now this sample of soil is subjected to triaxial test. Then what will be the value of lateral pressure in the cell when total stress during failure is 300 kN per meter square? I'll repeat the question once. A cohesive soil has an angle of shearing resistance of 15 degree and a cohesion of 35 kN per meter square. If a specimen of this soil is subjected to a triaxial compression test, find the value of the lateral pressure in the cell for failure to occur at a total stress of 300 kN per meter square. Next question. Laboratory results have shown laboratory results have shown that the unconfined compressive strength of a soil sample is 1.2 kg per centimeter square. In a triaxial compression test, a specimen of the soil, when subjected to a chamber pressure of 0.4 kg per centimeter square, failed at an additional stress of 1.6 kg per centimeter square. Estimate the shear strength of the same soil along a horizontal plane at a depth of 4 meter in a deposit. The groundwater table is at a depth of 2.5 meter from the ground level. Take dry unit weight of the soil as 1.7 gram per cc and specific gravity as 2.7. So we are asked to find out the shear strength in field condition using the test results obtained from the laboratory experiments. Now, in unconfined compressive strength test, the unconfined compressive strength is 1.2 kg per centimeter square. The same soil have been subjected to triaxial compression test. The same soil has been subjected to triaxial compression test at a chamber pressure of 0.4 kg per centimeter square. It failed at an additional stress of 1.6 kg per centimeter square. Now estimate the shear strength of the same soil along a horizontal plane at a depth of 4 meter in a deposit. Chamber pressure 0.4, additional stress of 1.6. The formation is the depth of 4 meter and the groundwater table is the depth of 2.5 meter from the ground surface. Dry unit weight is 1.7 gram per cc and specific gravity is 2.7. I'll repeat the question once. Laboratory test results have shown that the unconfined compressive strength of a soil sample is 1.2 kg per centimeter square. In a triaxial compression test, a specimen of the soil, when subjected to a chamber pressure of 0.4 kg per cm square, failed at an additional stress of 1.6 kg per centimeter square. Estimate the shear strength of the same soil along a horizontal plane at a depth of 4 meter in a deposit. The groundwater table is at a depth of 2.5 meter from the ground level. Take dry unit weight of the soil as 1.7 gram per cc and specific gravity as 2.7. Next question. When an unconfined compression test is conducted on a cylinder of soil, it fails under axial stress of 1.2 kg per centimeter square. The failure plane makes an angle of 50 degree with the horizontal. Find the cohesion and angle of internal friction of the soil. This sum is exactly the same as one sum from the last day. If anyone remembers, they can solve it very quickly. Two things are given. The axial stress at failure during an unconfined compression test is 1.2 kg per cm square, and the failure plane angle with the horizontal, that is 50 degree over here. To find out only the cohesion and the angle of internal friction of the soil. When an unconfined compression test is conducted on a cylinder of soil, it fails under axial stress of 1.2 kg per centimeter square. The failure plane makes an angle of 50 degree with the horizontal. Find the cohesion and angle of internal friction of the soil. Next question. In a consolidated drained triaxial test, a specimen of clay fails at a cell pressure of 60 kN per meter square. The effective shear strength parameters are C dash equals to 15 kN per meter square and phi dash equals to 20 degree. Determine the compressive strength. The type of test is given, the cell pressure has been given, and the C dash and phi dash values have been given to find out the compressive strength. And what does compressive strength mean in the case of a triaxial strength test? I'll repeat the question once. In a consolidated drained triaxial test, a specimen of clay fails at a cell pressure of 60 kN per meter square. The effective shear strength parameters are C dash equals to 15 kN per meter square and phi dash equals to 20 degree. Determine the compressive strength. Okay, next question. A given saturated clay is known to have effective strength parameters of C dash equals to 10 kilopascal and phi dash equals to 28 degree. A sample of this clay was brought to failure quickly so that no dissipation of the pore water pressure could occur. At failure, sigma 1 dash equals to 60 kilopascal, that is the axial stress, total axial stress, and sigma 3 dash equals to 10 kilopascal, that is the confining stress, total effective axial stress, and the pore pressure at failure is 20 kilopascal. Determine the values of A, sigma 1 and sigma 3 at failure, that is the total values of axial stress and cell pressure. the effective normal stress on the failure plane. What is the value of effective normal stress on the failure plane? And part C, the undrained shear strength. I'll repeat the question once. A given saturated clay is known to have effective strength parameters of C dash equals to 10 kilopascal and phi dash equals to 28 degree. A sample of this clay was brought to failure quickly so that no dissipation of the pore water pressure could occur. At failure, sigma 1 dash equal to 60 kilopascal and sigma 3 dash equals to 10 kilopascal is the effective stress, axial and the cell pressure, and UF, that is the pore pressure at failure, is 20 kilopascal. Determine the values of A, sigma 1 and sigma 3 are the total values of the axial stress and the cell pressure at failure. Part B, effective normal stress on the failure plane, and part C, the undrained shear strength. Next question. Two identical soil specimens were tested in a triaxial apparatus. First specimen failed at a deviator stress of 770 kN per meter square when the cell pressure was 200 kN per meter square. Second specimen failed at a deviator stress of 1370 kN per meter square under a cell pressure of 400 kN per meter square. Determine the value of cohesion and friction angle. If the same soil is tested in a direct shear apparatus with a normal stress of 600 kN per meter square, estimate the shear stress at failure or the shear strength. So we have two identical soil sample. The first one we have been given the deviator stress and the cell pressure, and the same thing are given for the second sample also. To find out the cohesion and the angle of friction, and using the values in the direct shear apparatus, when the normal stress is 600, what will be the value of shear stress at failure? I'll repeat the question once. Two identical soil specimens were tested in a triaxial apparatus. First specimen failed at a deviator stress of 770 kN per meter square when the cell pressure was 200 kN per meter square. Second specimen failed at a deviator stress of 1370 kN per meter square under a cell pressure of 400 kN per meter square. Determine the value of cohesion and friction angle. If the same soil is tested in a direct shear apparatus with a normal stress of 600 kN per meter square, estimate the shear stress at failure. So, three things need to be found out in this question: the value of cohesion, the friction angle, and using those values to find out the shear stress at failure in a direct shear box test when the normal stress is 600 kN per meter square of the same soil specimen. Okay, next question. What is the shear strength in terms of effective stress on a plane within a saturated soil mass at a point where the total normal stress is 295 kilopascal and the pore water pressure is 120 kilopascal? The effective shear strength parameters are C dash equals to 12 kilopascal and phi dash equals to 30 degree. So we have to find out the shear strength in terms of effective stress within a saturated soil mass. Total normal stress is 295 kilopascal and the pore water pressure is 120 kilopascal. The effective strength parameters are C dash equals to 12 kilopascal and phi dash equal to 30 degree. So normal stress is given, pore water pressure is given. We have a formula of shear strength with respect to the normal stress that also has the C and phi parameters. We can use that and find out the shear strength. It's a simple question. Normal stress is 295 kilopascal and the pore water pressure is 120. C dash, that is the effective cohesion is effective cohesion is 12 kilopascal and effective friction angle is 30 degree. I believe this question is self-explanatory. What is the shear strength in terms of effective stress on a plane in a saturated soil mass? I hope the question is clear. I'll go to the next question. A CU triaxial compression test, CU means consolidated undrained, was performed on a saturated sand at a cell pressure of 100 kilopascal. The ultimate divider stress was 350 kilopascal and the pore pressure at peak stress was minus 40 kilopascal, that is suction. Estimate the total and effective shear strength parameters. Now, in a consolidated undrained triaxial test performed on saturated sand, the cell pressure is sigma 3 is 100 kilopascal and the ultimate deviator stress at failure was 350 kilopascal when the pore pressure at that peak stress was minus 40 kilopascal. So, since the pore pressure is also given, we have to find out the total and the effective shear strength parameters. I'll repeat the question once. A CU triaxial compression test was performed on a saturated sand at a cell pressure of 100 kilopascal. The ultimate deviator stress was 350 kilopascal and the pore pressure at the peak stress was minus 40 kilopascal, which is suction. Estimate the total and effective shear strength parameters. So this was the last question. If anyone joins, they can, anyone have copied the question, they can start solving. So I have dictated all the questions and I'll take some time. If anyone has joined, they can start writing the questions, that is the solutions. I'll join after a while and start discussing the solutions. Okay, I'll be starting to discuss the solutions right now. The first question was a cylindrical sample of soil having cohesion. Okay, the cohesion was given, friction angle was given, cell pressure was given, maximum deviator stress, sample will fail. Okay, so the formula is for a triaxial test sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. Sigma 1 equal to sigma 3 tan square alpha plus 2 3 tan alpha 2c tan alpha. So here sigma 3 has been given over here. The cell pressure is 1 kg per centimeter square. C is given and phi is given. As we know, alpha equals to 45 plus phi divided by 2. I get the value of alpha. We get the value of alpha as 55 degree. Yes, 20 by 2. 20 by 2, 10 plus 45, 55 degree. 55 degree is the value of alpha. Now, using this equation, you can find out sigma 1, that is the axial stress, total axial stress, that is equal to sigma 3 is given 1 into 10 square alpha plus 2 into c coefficient to 10 alpha. Sigma 1, the value of sigma 1 we get as, we will get 4.32. We get 4.32 kg per centimeter square. We get 4.32 kg per centimeter square. Now we are asked to find out the deviatory stress. So deviator stress, that is sigma d that is equals to total axial stress sigma 1 minus cell pressure sigma 3. So 4.32 minus 1 will get 3.32 kg per cm square. In the next case, we are asked to find out the angle made by the failure plane with the sample axis. Now, if this is the failure plane, this is the angle by the failure plane. This is equals to alpha. This is the major principal plane. This is the sample axis. It will be, the sample axis will be 90 minus alpha. That is, angle made by the failure plane will be, if we say alpha sample axis is equals to 90 minus alpha, equal to 90 minus alpha. That will be equals to how much? 90 minus 55, 90 minus 55 degree equals to 35 degree. Yes. So in this question, the maximum deviator stress at failure is 3.32 kg per centimeter square, and the angle made by the failure plane with the axis of the sample is 35 degree. I hope it was clear. Next question. An embankment 5 meter high. Yes. So in this question, we have to find out the shear strength at the base of the soil. So first of all, due to increment in the height, there will be an increment in the vertical stress, sigma 1. If we consider sigma 1, it is equal to gamma into change in height, del H. Gamma into del equal to 16.2 into 8 minus 5. 16.2 into 3 equals to 48.6. 48.6. What is the value? Value will be in kilonewton per meter square. Now it has been said that lateral pressure is half of the vertical pressure. So what is the change in lateral pressure? Del sigma 3 equals to half of del sigma 1, 24.3. Now, using the Skempton's pore pressure parameters, you can find out the increment or decrement, whatever, in the pore pressure. That will be equal to parameter B into del sigma 3 change in cell pressure plus parameter A into del sigma 1 change in axial stress minus del sigma 3 change in pore pressure. And that value we know A and B, we know del sigma 1, del sigma 3. Putting in this equation, we get the value approximately equal to 31.3. 31.3 kilonewton per meter square. I believe the gamma value would be in kg, not in kg. It will be in kilonewton per meter square. That will give you that directly the result kilonewton per meter cube. So here we have 16 kilonewton per meter cube, 16.2 into 16.2 kilonewton per meter cube. Okay. Yes. So now we have to find out the original pressure. What is the original pressure? Initially the height was h0. Initially the height was 5. 16.2 into 5, that will give us 81 kilonewton per meter square. Now we can find out the effective stress. What is the effective stress? The decrement, the pore pressure that has been coming into consideration, that has been subtracted, along with, if we write like this, equals to, initially it was sigma 1 plus the increment minus the change in pore pressure. Initial plus increment minus the change in pore pressure. So change in pore pressure 31.3, initial 81, and del sigma 1 is 48.6. Put in the value, we get approximately around 98.3. 98.3 kilonewton per meter square. Now in this formula, tau equal to C dash plus sigma dash tan phi dash. Sigma dash tan phi dash. C dash equals to 50, phi dash equals to 16 degree, and sigma dash equals to 98.3. We get a value of 78 78.19 kilonewton per meter square. So first of all, we find out the increment in the vertical stress. Then within the half of the value, we find out the increment in the cell pressure or horizontal stress or lateral pressure. Now in the formula B into del sigma 3 plus A into del sigma 1 minus sigma 3, find out the increment in the pore pressure. Now the initial on the initial value of the axial stress, we add the incremented value of axial stress and subtract the pore pressure. Change in pore pressure, we get the effective stress at the base of the embankment. Using this effective stress sigma dash and the effective values of C and phi, tau equal to C plus sigma tan phi. Here we get tau equal to C dash plus sigma dash tan phi dash. We put the value in its position and we get a value of 78.19 as the shear strength of the soil at the base of the embankment, just after the soil has been raised from 5 meter to 8 meter. I hope it was clear. Okay, this question. So in this question also we have been given a deviatoric stress of 482 and sigma 3 cell pressure is initially given as 100. Now cohesionless sand is given, so C equal to 0 we all know. Now the equation is sigma 1 equals to sigma 3 tan square alpha plus 2C tan alpha. Sigma 3 tan square plus 2C tan alpha, and also here we can write like this: sigma 3 tan square alpha plus 2C alpha will not come into consideration because C is 0. The value of C is 0 by here. Also sigma 1 equals to sigma 3 plus sigma D. Sigma D is 482, sigma 3 is 100, we get a value of 582. 582 kilonewton per meter square. Now using this we get alpha equals to tan inverse root over of sigma 1 by sigma 3, because tan square alpha equals to sigma 1 by sigma 3. Now from there we get the value of alpha. If we substitute, we get a value of alpha 67.485 approximately 67.485 degree, from which we can get phi. Why? Alpha equals to 45 plus phi by 2. So phi equals to 67.485 minus 45 into 2. We get a value of approximately, the value of phi will be approximately equals to 44.97 degree, almost equals to 45 degree. Okay. Now another identical specimen has been taken into consideration where sigma 3 is 200 kilonewton per meter square. For this another specimen, what we can do, we can again calculate we have tan square alpha. Now what is the value of tan square alpha over here? Using this equation, sigma 1 equals to sigma 3 tan square alpha, and sigma 3 is been given over here 200 and alpha is the same as 67.485. So sigma 1 we can obtain like this. It will give us 200 into 5.82 is 1164, approximately 1164 kilonewton per meter square, sigma 1. Now what is the deviatoric stress? That is sigma D will be equal to this major principal stress sigma 1 minus sigma 3, that is the value 1164 minus 200 will give us 964 kilonewton per meter square. So first of all, the cohesion will be equal to 0. The equation simplifies into a smaller equation from which you can get the value of alpha and corresponding to the value of phi. In the same equation, sigma 1 equals sigma 3 tan square alpha, we can find out sigma 1 for the new cell pressure, and then the divisory stress equals to major minus minor. We get the value of the divisory stress as sigma 1 minus sigma 3. I hope it is clear. I go to the next question. Consolidated undrained test. Okay. So here also we have been given the value of sigma 3 and sigma t, but we can find out the value of major principal stress, that is sigma 1 equals to sigma 3 plus del sigma d. Del sigma df and sigma d are same thing at failure. If we consider 250 plus 275, we get value of 525 kilonewton per meter square. Now we have been given, that is, undrained test on normally consolidated clay. So for undrained test, that is, the soil is not being allowed to pass out after consolidation. For this kind of test on normally consolidated clays, the value of C will be equal to 0 as per the triangular testing condition. As per triangular testing condition, for consolidated undrained triangular test or any kind of undrained test or normally consolidated clays, any kind of test, undrained test, non-consolidated clays, the C is 0. So again the sigma 1 equation changes to sigma 3 tan square alpha. So cohesionless soil and undrained test on normally consolidated clays, C becomes 0 and the equation becomes sigma 1 equals to sigma 3 tan square alpha, from where we get the value of alpha. Sigma 3 we have already given. We get the value of alpha as equal to 55.4 degree, and the value of corresponding value of phi is equals to 45 minus pi by 2, that is alpha equal to 45 minus pi by 2, 55.4 minus 45 into 2, 20.8. Yes, the value of phi is 20.8 degree. So angle of friction is being obtained. Angle made by the failure plane on the major principal plane is obtained. This value of alpha and phi we have been obtained. And now what we need to find out? We need to find out normal stress and shear stress on the failure plane. Now the formula for normal stress on the failure plane is, with respect to any concepts of solid mechanics, sigma, the normal stress, equals to sigma 1 plus sigma 3 by sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 alpha. This is the value of normal stress, and the value of shear stress is tau equals to sigma 1 minus sigma 3 by 2 sine 2 alpha, twice the failure angle, sine 2 alpha. Sigma 1 is the major principal stress and sigma 3 is the minor principal stress. So major plus minor by 2 plus major minus minor by 2 into cos 2 alpha gives us a normal stress on the failure plane, and for shear stress we get major minus minor divided by 2 into sine 2 alpha for the shear stress on the failure plane. So sigma 1 we have got 525, sigma 3 250, alpha is 55.4. Putting all these values over here, we get the value of normal stress on this failure plane as, the normal stress as 338.338.67 approximately in terms of kilonewton per meter square, and for shear stress the value we get is 128.54 kilonewton per meter square. So in this way we can obtain the normal stress and shear stress on the failure plane in a particular soil mass. I hope it is clear. I'll go to the next question. Particular soil with major principal stress of 300 corresponding minor principal stress of 100. Okay. So the main equation, the primary equation, sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. Now, for the first case, for case A, when phi equal to 30, alpha will be equal to, for first case, alpha will be equals to 45 plus pi by 2, 30 by 2, 50, but it equals to 60 degree. Alpha will be equal to 60 degree. Using this value, we have major principal stress 300, minor principal stress 100, that is sigma 1 equal to 300, sigma 3 equals to 100, and 2c tan alpha. Placing everything in this equation and the value of alpha, we can find the value of c in the first place. We find the value of c in the first place. In the first case, c gives the value of 0. C gives the value of 0. So sigma 1 equals to again sigma 3 tan square alpha. Now using this equation, in the second part it has been said that the minor principal stress has been 200. Find the major principal stress. So obviously if now sigma 3 is 200, sigma 1 will be how much? 200 into tan square alpha. Alpha is 60 degree. Tan 60 is root 3. Tan square 63. 200 into 3 is 600. It will be equal to 600 kilonewton per meter square. In the second case, in part B, phi equal to 0. So alpha equals to 45 degree. 45 degree. In this equation, sigma 1 equal to sigma 3. Sigma 1 is 300, sigma 3 is 100. Alpha equals to 45 degree. We can find out the value of c. C here is equals to, after rearranging and placing them, find c is equals to 100 kilonewton per meter square. So sigma 1 equals to sigma 3 tan square alpha is 45 degree plus 2 into 100, 2 into 100, 2c tan phi, 2c tan alpha, tan 45 degree. This is the equation. Now placing sigma 3 as 200 in the second case. In the second case, sigma 3 is 200. We get a value of sigma 1 as, okay, tan 45 is 1, is 200 plus 2 into 100, 200 is gives us 400. Very simple. So the main equation, sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha, we use in the two separate cases to find out alpha and the corresponding value of cohesion. Using the modified equation, we find out the value of the major principal stress for the change value of the minor principal stress. I hope it is clear. I go to the next question. Okay, so here the percentage strain is given. It is a very easy question. So this is the percentage strain, means change in dimension by original dimension. This change in length by original length, that is given over here as 10% is 0.1. So change in cross section of the sample means the change area at failure will be equal to the original area of cross section divided by 1 minus the strain. 1 minus the strain. What is the original area of cross section? Pi by 4 d square. Pi by 4 into diameter is 50 mm whole square, that is equals to almost will give us, okay, no need to find this out. You put the entire thing in this equation, and then the value of change cross section area after failure is 2181, almost equal to 218, pardon, 2181.7 mm square. Now you have to find out the shearing resistance or the shear strength. But this is an unconfined compression test. First we will find out the compressive strength. The unconfined compressive strength is equals to the load at failure, that is 150, divided by change in cross section area, because it is say taking into account the change in cross section. So AF 150 Newton divided by this. So this gives us approximately equal to 0.06785. If we convert this, it will get around 68.75. 68.75 kilonewton per meter square. Kilonewton per meter square. This is the value of compressive strength. Now in unconfined compression test, the shear strength, that is undrained cohesion or shear strength, is equals to, as I discussed in the previous session, QU by 2, or it is equals to approximately 34.38 kilonewton per meter square. Unconfined compression strength means undrained shear strength is equals to half of the compressive strength, that is Cu equals to Qu by 2. I hope it is clear. I'll go to the next question. This is also a very easy question. The water table is at a depth of 3 meter. The shear strength on the horizontal plane at a depth of 2.5. Now we need to find out gamma to find out the normal stress. Now when water table is at depth of 3 meters, that is part A. This part A, gamma equals to G plus SE gamma W divided by 1 plus E. Now G we have been given, S we have been given, void ratio also we have, and gamma W we can take that as 9.81. Gamma W we can take it as 9.81. We get a value of 19.293 kilonewton per meter cube. Now to find out sigma, because water surface is below the level, sigma equals to gamma into H, that is gamma into 2.5, we get 48.23, approximately 48.23 kilonewton per meter square. Now tau, what is the value of tau? Tau equals to C plus sigma tan phi. C plus sigma tan phi. Here the value of phi is given. The value of cohesion is given because it is a cohesionless soil in this question. Yes, so position will be equal to 0, we get a value of shear stress. And yes, this stress is the effective stress because it is dry, so this sigma is obviously equal to sigma dash. We get the value of 48.23 into 10 30 degree friction angle, 27, approximately 27.85 kilonewton per meter square. Now in part B, in the same thing, however, we need to find out gamma sat. Gamma in terms of gamma sat. Gamma in terms of gamma sat. So we see that at when the water table is at the ground surface, when water table is at the ground surface, in the same formula, that is the G plus SE by 1 plus E, the average friction of the soil, that's the value of gamma sat. The moisture content value will change over here. In this case, the value of the moisture content will change over here, and if it is fully saturated, then this S value will be equals to 1 and not 0.5. This S value will be equals to 1. So in this case, if we calculate G plus E divided by 1 plus E into gamma W, 2.7 plus the value of E 0.5 into 9.81 divided by 1.5, we get a value of 20.928. This gamma sat 20.928 kilonewton per meter cube, and hence gamma submerged will be equals to gamma sat minus gamma W, that is equals to 11.118 kilonewton per meter cube. Now if we have to find out the value of sigma dash at a depth of 2.5 meter, sigma dash will be equals to gamma submerged into H. Gamma submerged into H, that is 11.118 into 2.5, it will give us a value of 27.795. 27.795, and hence we can find out the value of tau equal to sigma tan phi. Tau, in the same equation, the value of tau will be getting as 16.05. I hope it is clear. The degree of saturation will change, and hence the value of gamma will change. Thus the normal stress will change and it will affect the shear stress. Next question. Okay, this is also a very easy question. We need to write down the first equation. Sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. Using this, now sigma 1 equal to sigma 3 plus sigma d. Sigma 1 equals to sigma 3 plus sigma d. So sigma 3 is 2 kg and sigma d is 7.7. So sigma 1 for the first case is 9.7. 9.7 equals to sigma 3. Control set. Sigma 1 is 9.7 equals to sigma 3, that is 2 tan square alpha plus 2c tan alpha. And again in the second case it is 5 and 13.7, that is 18.7. 18.7 equals to 5 tan square alpha, 5 tan square alpha plus again 2c tan alpha. Now this is two equations in two unknowns. We'll solve it simultaneously to get the value of tan alpha, and then we get a value of 5. Now if you solve this, we get a value of tan alpha equals to 1.732 1.732, from which alpha equals to 60 degree, alpha equals to 60 degree, or phi equals to alpha equals to 45 plus 5 by 2, 15 into 2, 30. Yes, 30 degree. Phi equals to 30 degree, and corresponding the value of C, if we place alpha, we get approximately around 1.068. If you place in any equation 1 or 2, 1.068 kg per centimeter square. So this is the value of C and the value of phi. Question the angle of internal friction. I hope it is clear. I go to the next question. Cohesive soil, angle of shear in C. Yes, this is also a very easy question. Again, the same equation. Sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. Now, alpha equals to 45 plus 5 by 2. Since alpha equals to how much? 45 plus 5 by 2, it is 52.5. 15 by 2, 7.5, 52.5. Yes. Degree. So, we are asked to find out the cell pressure. So, in this equation, if we put the value of sigma 1 as 300, sigma 1 equals 300, 300 equals to sigma 3 tan square alpha plus 2c tan alpha, alpha 52.5 degree, sigma 3 we need to find out, and this is 300, 300, and C, the value of C is 35. We get, rearranging the values, we get sigma 3 as equals to, sigma 3 equals to around 122, yes, 122.96. 0.96 kilonewton per meter square. Easy question, very easy question. I'll go to the next question now. Okay, so here first unconfined compression test has been done, and here sigma 1 we know sigma 1 equals to 2c tan alpha, because it is unconfined, sigma 3 is 0. Hence, we can say that here sigma 1 is 1.2. It has been said it is a compressive strength 1.2 equals to 2c tan alpha. Next comes the triangle test. In the triangle test, we get sigma 1 equals to sigma 3 plus sigma d. Sigma 1 equals to sigma 3 plus sigma d. Sigma 3 is 0.4 and sigma d is 1.6. We get the value of 2. That is 2 kg per cm square. 2 kg per cm square. Now, in this case, in triaxial testing, sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. Now, 2c tan alpha value we already know, that is equals to 1.2. This one equals to 1.2. And sigma 1, the value of sigma 1 we know. From here, we can find the value of alpha, because sigma 3 also we know. Sigma 3 is 0.4. Sigma 3 is 0.4. The value of alpha we get from here is equals to 54.74 degree, and hence the corresponding value of phi is approximately 19.47 degree. 19.47 degree. Now we have to find out the shear strength of a formation. Now, in this case, if we find the value of alpha and putting the same in equation 1, we find C, that is the cohesion, equals to 0.424. 0.424 kg. If we convert it into tons, we can do it for the sake of simplicity. 4.24 ton per meter square, value of cohesion. Now, since it has been said that there is a water table at a depth of 2.5 meter, so at a depth of 4 meter, the first 2.5 meter will be dry and the next 1.5 meter will be submerged unit weight. So, if you want to find out the value of submerged unit weight, you can use a formula, that is gamma submerged equals to G minus 1 by 1 plus E gamma W. Now G, the value of G is I think given, yes, 2.7, 1 plus E. Now how to find out the value of E? You can find out the value of E. Okay, gamma W is not 9.8 over here because it is gram per cc. It is equals to 1. So over here, E will be equals, I'll write in the side. E is equals to G gamma W by gamma D minus 1. G gamma W by gamma D minus 1. So gamma D over here is 1.7 gram per cc. So gamma W will be 1 gram per cc. You can find out the value of E. The value of E is 0.588, almost equal to 0.588. The value of gamma submerged is equals to 1.07 ton per meter cube. 1.07 ton per meter cube. Ton per meter cube. So in this case, we can find out the effective stress sigma dash as the first 2.5 meter is dry, so 2.5 into 1.7, 2.5 into 1.7 plus the next 1.5 meter is submerged into 1.5 into 1.07. We get the effective stress as 5.855. 5.855 ton per meter square. Ton per meter square. Now using the same formula, tau equals to C plus sigma dash tan phi. Phi is 19.47. C is 4.24 ton per meter square and sigma dash is 5.855. We get the value of shear strength at 4 meter depth as equals to 6.31 ton per meter square. This is the answer. Same question, just a bit lengthy. I hope it was clear. I go to the next question. Yes. Where unconfined compression test. This is very simple. First of all, we have alpha equals to 45 plus 5 by 2 equals to 50 degree. So the value of phi will be equals to how much? The value of phi will be 50 minus 45 is 5 into 2, 10. Value of phi is 10 degree. Value of phi is 10 degree. Again, unconfined compression test. So sigma 1 equals to sigma 3 is 0. So it is only equal to 2c tan alpha. From here, c equals to sigma 1 divided by 2 tan alpha. Sigma 1 divided by 2 tan alpha. Sigma 1 is 1.2, 2 tan alpha is 50 degree, alpha is 50 degree. So the value we get is approximately equal to 0.503. In the same unit as sigma 1, that is kg per cm square. A simple easy question. It was there in the last session also. Just for the sake of reference, I've given it here. Okay, fine. Next question. Consolidated drain test, drain triaxial test. Okay. Again, we have been given the C, the phi, and the cell pressure. So from this phi value, we can find out the value of alpha is 45 plus 5 by 2. Phi is 20, 45 plus 20. This gives us a value of 55 degree. Angle of the failure plane with the major principal plane. So we can get the value of sigma 1. Sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. We have the value of alpha with the value of c and the value of sigma 3 is 60. Put in the values, we get sigma 1 equals to 165.24. Yes, 165.24 kilonewton per meter square. Now we have to find out the compressive strength. Now, if this is the sample, if this is the stress given from the top, the stress from the top, and the overall stress, that is like this, the stress is sigma 3. So sigma D equals to sigma 1 minus sigma 3, at which sigma 3 it fails, it becomes the compressive strength. So we can say that the diabatic stress at failure is the compressive strength of the soil sample. So diabatic stress at failure, what is that? That is equals to sigma 1 minus sigma 3. That is 165.24 minus 60. We get 105. We get 105.24 kilonewton per meter square. This is the compressive strength of the soil sample, which is equal to the diabatic stress at failure. I hope it was clear. I go to the next question. Saturated clay, determine. Okay, sigma 1 and sigma 3 is very easy to find out. Sigma 1 equals to sigma 1 dash plus uf, which is equals to 60 plus 20 is 80 kilopascal. Similarly, sigma 3 equal to sigma 3 dash plus uf, that is 10 plus 20, that is 30 kilopascal. The effective normal stress on the failure plane. Effective normal stress, for which we will be using the effective stress parameter, that is the sigma dash is equals to sigma 1 dash plus sigma 3 dash divided by 2 plus sigma 1 dash minus sigma 3 dash by 2 cos 2 alpha. Cos 2 alpha. We get a value of approximately 23.26. 23.26 kilopascal. Now, in the case of undrained shear strength, there is a twist over here. Why? Because in the case of undrained shear strength, the parameter being considered over here is phi equal to 0. Is phi equal to 0. Hence, the undrained shear strength is equals to the undrained cohesion of the soil. The undrained shear strength is equal to the undrained soil cohesion, and in this case we use the total stress parameter, for which the equation becomes sigma 1 and not sigma 1 dash equals to sigma 3 tan square alpha plus 2cu tan alpha, from which the value of cu, or the undrained cohesion, here sigma 1 is 80, sigma 3 is 30. Whoever has joined, this is the end, almost the end of the session. You can just have a look at the solutions, from which the undrained value of the cohesion, that is the undrained shear strength, is equals to approximately equals to 25. Yes, 25 kilonewton per meter square. 25 kilonewton per meter square. In the undrained shear strength conditions, the phi equal to 0, the shear strength equals to undrained cohesion, and the total stress parameters would be used. Okay. Next question. Two identical soil specimens. This is similar to the last question, in which in the first case sigma 1 we have to find out sigma 3 plus sigma t, that is equal to 720 plus 200, 970, almost 970. Yes. I am saving the units right now. Sigma 3, not sigma 3, control Z. Sigma 1 for the next sample is 1370 plus 400, this is 1770. 1770. So the equations are 970 equals to sigma 3, that is 200 tan square alpha plus 2c tan alpha, and 1770 equals to 400 tan square alpha plus 2c tan alpha. Solving these equations, we get the value of c and phi. First, we get the value of alpha, from which phi. I have shown in the previous questions how to obtain phi using alpha, 36.87 degree, and the value of c we get as 42.5 kilonewton per meter square. Hence, if we use these parameters in the shear box test, tau equals to c plus sigma tan phi, and the value of normal stress is 600. The value of sigma is 600. We get tau in the direct shear box test as 42.5, that is c plus sigma 600 into tan 36.87. We get 492.5 kilonewton per meter square. The value of shear stress at failure in direct shear apparatus or the shear strength. Next question. Okay, shear stress in terms of effective stress. Yes. So effective stress, the value of effective stress is total stress minus the pore pressure is 295 minus 120, and gives us value of 175 kilo Pascal. Hope it is clear. 175 equals to 175 kilo Pascal. Now shear strength, effective shear strength equals to C dash plus sigma dash tan phi dash, where C dash equals to 12, yes, sigma dash equals to 175, and phi dash equals 30 degree. Get a value of approximately 113.04 kilo Pascal. Tau equal to C dash plus sigma dash tan phi dash in case of effective stress parameters, 103.04. Okay. Last question. Here we can find out the value of sigma 1 first using the value of sigma 3 plus sigma d, that is 100 plus 350, that is equals to sigma 3 plus sigma d. Sigma 3 is 100 plus 50 equals to 450 kilo Pascal. Now, what is the effective strength parameters? Effective sigma 1 equals to sigma 1 minus u. Now u is actually negative, so sigma 1 minus plus 2. So 450 plus 40 is equals to 490 kilopascal. And again sigma 3 dash, that is equals to sigma 3 minus u. The sigma 3 is 100. 100 plus 40, that is equals to 140 kilopascal. Now, trial shear compression test performed on a saturated sand. It is consolidated undrained test performed on saturated sand. So for saturated sand, we know for sand cohesionless soil C equal to 0. C equal to 0, we need to find out only the value of phi, and the formula is, in the case of total stress parameters, sin phi equals to sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3, from which we can get, this is the total stress, sigma 1 equals to 450 and sigma 3 equals to 100, this sin phi. We get the value of phi, that is the total shear strength parameter phi, as 39.52 degree. For the effective parameters, that is sin phi dash equals to simple sigma 1 dash minus sigma 3 dash divided by sigma 1 dash plus sigma 3 dash. From here value of phi dash also we can obtain. Sigma 1 dash is 490, sigma 3 dash is 140. We get the value of phi dash as 33.75 degree. 33.75 degree. So the total stress parameter concerning the angle of friction is 39.52 degree, and the effective angle of internal friction is 33.75 degree. I hope it was clear. Thank you for attending the session. We will be meeting next on the coming Sunday with the next lecture of week 8. Thank you so much.